This lesson is going to be taking a look at how to translate other functions. We've already previously looked at how to translate quadratic functions, so we're going to look at how to translate or to slide other different types of functions that we have looked at throughout this year. So if we take a look at this particular function, the first one says the parent function is y equals x. We should know that that is a linear function because it's technically in slope-intercept form. Slope-intercept form, if you recall, is in the form y equals mx plus b, where b is the y-intercept and m is your slope. So the parent function, y equals x, technically then I could say that that's x plus 0. So my y-intercept, if I make my graph larger, would be at the origin 0, 0. And then my slope is before the x, and there's no coefficient there, so we assume that it's 1. So that means then that we're going to rise 1 and run 1. So I'm going up 1 to the right 1, up 1 to the right 1, all the way across the entire grid to make my line. And then to get to the other side, I'm going down 1 and to the left 1. And then I can connect it to make my straight line, and then I have my original parent function or my linear function. If we slide it over, the next function so it's translated is y equals x plus 2. So what changed there is our y-intercept, because that was what our b is. So it's plus 2. So that means it takes every point on this line and it shifts it 2 up, or basically it changes my y-intercept to 0, 2 instead of 0, 0, and then my slope is still up 1 over 1. So I'm still going up 1 over 1. And then on the other side, I'm going down 1 to the left 1. And what you should notice once I connect all of these red points is that the red line and the black line are parallel because they have the same slope, but they do not have the same intercept. And then the last line that we're going to look at translate should say y equals x minus 4. So that's going to take this and shift this entire line 4 units down. So if we start from our original and I go 4 down, that would make my intercept negative 4, which makes sense because it's y equals x minus 4. So 1, 2, 3, 4. And then the slope is still the same, so it's up 1 over 1 every single time. And then down here again, it's down 1 to the left 1. And then I can connect it, and you should see that that blue line is also parallel to the red and the original black line. So to translate a linear function, we're really only looking at translating it up and down for the most part. And to do that, you just have to change the value of your y-intercept. The next page is the quadratic function. I'm not going to spend time in this video just detailing how to translate a quadratic function because we have already done a whole entire lesson on how to do that. So if you need help with translating a quadratic function, please reference that video as well. This parent function, y equals 2 to the x power, is an exponential function. And remember, when we graphed exponential functions, we started by making a t-chart. So if I want to make my t-chart, I have x and I have y, and I'm going to go to the values -3, -2, -1, 0, 1, 2, and 3. So I want to make my x value the exponent. So if I start at the bottom and fill in my table, 2 to the third power is 8 because 2 times 2 times 2 is 8. 2 to the second power is 4. 2 to the first power is 2. 2 to the 0 power, remember anything to the 0 power is always 1. And then when we have negative exponents, that takes the values that we already have as the exponents and sends them to the denominator of a fraction. So 2 to the -1 power would be the fraction 1/2. 2 to the negative second power would be the fraction 1/4. And 2 to the negative third power would be the fraction 1/8. So if I take the graph and make it larger, to graph these, we have 3, 8. We have 2, 4. 1, 2, 0, 1, -1, 1/2, -2, 1/4, -3, 1/8. So as you notice, our line should curve and get exponentially closer to that 0 point, but will never actually cross that. The next function we're going to look at, if I make my screen smaller, is y equals 2x. So it's 2 to the x power. So this is just still the same, but it says plus 2. So the plus 2, just like with the linear function, is going to take this entire thing and shift it 2 units up. So all I have to do is take my points and add 2 to them. So I had 3, 8. So if I add 2 to that, it's going to become 3, 10. Then I have 2, 4, which would become 2, 6. They then had 1, 2, which would become 1, 4. I had 0, 1, which would become 0, 3. I had negative 1, 1 half, which would become negative 1, 2 and a half. Then I have negative 1, 2 and a fourth, negative 1, 2 and an eighth. So this time it gets exponentially close to the 2 line instead of the 0 line. So that takes it up and it shifts it exactly 2 units up. The next graph on here would be the same function, y equals 2 to the x power, but it's minus 4. So that one would have taken the original function and it would have subtracted 4 from each value, and it would have shifted it 4 units down. Instead of doing that one, I'm going to take a look at something. What would happen if we graphed the function, instead of y equals x, or 2 to the x power minus 4, if we did something else? What if we said something like y equals 2 to the x minus 2 power? If we did it that way, notice this time the minus 2 is inside the parentheses. So let's take a look at what that would actually do. That would take our exponent and it would subtract it by 2. So if I had still my original table, so I have my x and my y, right, and I have negative 3, negative 2, negative 1, 0, 1, 2, and 3. So if I say 2 to the third power, but it's really minus 2, 2 to the third minus 2 really is 1, right? Because 2 to the first power then is 2. I would have 2 to the second power minus 2, which would be 2 to the 0 power, which would give me 1. 2 to the first power minus 2, right? So 1 minus 2 gives me negative 1. So that would be the 1 half. This would be the 1/4, the 1/8, etc. So notice this time it's taking our entire graph and it's moving it. So if we did this, I'm going to put it here. I have the point 3, 2. So 1, 2, 3, 2, 2, 1. 1, 1 half, 0, 1/4, negative 1, 1/8. So it still gets exponentially close to that 0, just like the black line did, but it's moving it over, and it's moving it to the right instead 2 spots, because it would end up going up like this, and it's moving our graph to the right instead of up or down. So when you're adding or subtracting something in the parentheses where it's your exponent, that's what moves it left or right. This time I want to take a look at the absolute value y, or the absolute value function y equals the absolute value of x. So if we graph this, remember the absolute value is the distance that a particular number is from 0. So if I made a chart, right, and if I made kind of a t-chart just like we did in the other one, if I did negative 3, negative 2, negative 1, 0, 1, 2, 3, right, if I made my t-chart that way, negative 3 is 3 spaces from 0, negative 2 is 2 spaces from 0 on the number line, negative 1 is 1 space, 0 is 0 spaces because it is 0, 1 is 1 space, 2 is 2 spaces, 3 is 3 spaces, etc. So when we graph these, if you recall, this looks like a V, because if I graph them and make my graph larger, I have negative 3, 3. Oops, that's not the right point. So if we graph again, negative 3, 3. 1, 2, 3, 1, 2, 3. Negative 2, 2. Negative 1, 1. 0, 0. 1, 1. 2, 2. 3, 3. Right? And if we connected them, it would end up going like this, and it would look like a V. So if we take a look at the function that we're going to translate, it says the absolute value of x plus 4. So what that is going to do is that is going to shift our entire thing up 4 units. So if I'm adding 4, the absolute value of negative 3 was 3, but plus 4 would become 7. So instead of negative 3, 3, it'd be negative 3, 7. Then the absolute value of negative 2 was negative 2. If I add 4 to that, I get 6. Then the absolute value of negative 1 was 1. If I add 4 to that, I get 5. The absolute value of 0 was 0, and if I add 4 to that, I get 0. And then if I add the absolute value of 1 was 1, if I add 4 to that, I get 5. Then I have 6 and 7 again. So it would look exactly the same. It would still be a V, except it was moved 4 units up. So if we take a look at the final one, this time the value is inside the absolute value symbol. So it says y equals x, or the absolute value of x minus 5. So just like with the exponential function, when it was inside the actual exponent, it made it go right or left. So this time, when it says the absolute value of x minus 5, it's going to move everything from our original function 5 units to the right. So if I graph this one, my original was negative 3, 3. So we're again taking our original, so we're looking at the blue, and we're moving every point 5 units to the right. So instead of it being negative 3, 3, right, I'm going to take and go 1, 2, 3, 4, 5, and that point's going to become here at 2, 3. Then I'm going to have negative 2, 2. So then the negative 2, if I added 5 to that, would become 3, 2. Then I had negative 1, 1. Negative 1 plus 5 is 4, so it'd be 4, 1. Then I had 0, 0, so that would be, adding 5 to it would be 5, 0. Then it would become 6, 1, because remember we're making the V, 7, 2, 8, 3, etc. So it would end up looking like this. So it took your value or your parent function and it shifted it 5 units to the right because the minus 5 was inside the absolute value symbol.